All right, hi everybody. This is going to be our first lecture in ISTM 313. We're going to do our introductory lecture on the database environment, make sure that everybody understands some of the basic definitions and principles behind the topics we'll be discussing throughout the remainder of the semester. As stated before, if you have any questions, please feel free to speak up and I will be happy to answer questions. You're also welcome to type any questions you might have in the chat, and I will try to switch over to that every once in a while and take a look if anybody has any questions and answer those there. So first, let's get some definitions out of the way. This class is dealing with how we manage data. And so one of the major tools we're going to be talking about throughout the semester is a database. And you've heard the term database used your entire lives. What do we mean when we talk about a database? The best way to think about a database is organizing data that has some sort of logical relationship. It's not just everything. It's a bunch of different data points that have something to do with one another. So as part of your experience here at Texas A&M, think about the information that our school needs about you. Specifically, I'm thinking what we need to know about you in terms of your enrollment in classes. That's a pretty easy one for all of us to imagine. So what we need to know about you is some personal information. We need to know your last name and your first name and your UIN and probably your local address, maybe your permanent address back home. We also then need to know what your major is. We need to know what classes you've taken in a given semester. We need to know what grades you got, how many credits those classes were. And then from a database that collects that kind of information, we could process things like your GPA, how far along you are, whether you're technically a sophomore or a junior or a senior, whether you have qualified for any minors or special certificates, whether you are ready to graduate or not. So the database would be information that is related to a specific topic. In this case, it would be students that are enrolled in classes at our university, Texas A&M. We wouldn't be collecting information that isn't relevant to that topic. So I probably wouldn't know things like your favorite color, what gaming console you own, what kind of car you have. Those sorts of things are certainly interesting data points about you, but they're not relevant to the database that we would be designing. And I'm making silly points to illustrate a really important point, which is that we definitely need to pay attention to scope when we look at databases. It is really easy to get carried away and think we could have all of this information and just pile it all in, and then we can kind of use it if we need to, and if we don't need to, we've got it. And to some degree, that is what big databases are doing. When you think about companies like Facebook, Amazon, and Twitter, they know all sorts of things about you. Some of them might be extraneous for some problems, but they might be useful for other problems. They just collect everything, and then they dig through it and figure out what they might need. That's not what we're going to be focusing on this class. In this class, we're going to be talking about databases that have a very specific focus, a very specific mission, and as a consequence, have very specific data that we are going to include and lots of data that we're going to leave off to the side. So we're only thinking about data that is relevant to a specific problem. And that's going to come around every time we work through our examples and work through some homework problems, even exams. What data is relevant and what data is irrelevant to the specific problem that we're trying to address. So we'll talk about that a lot more as we move through the semester. Data, as I keep mentioning, is some sort of representation of real things, objects, events. It could be prices. It could be, like I said, your GPA or your score on something. Data could be structured, like numbers and dates and texts, but it also could be something unstructured. Unstructured, we're typically thinking about things like images and videos and documents that are still associated with other structured data. So I might know lots of things about you, but I also have a snapshot picture of you from your ID here at Texas A&M, so I know what you look like. Or maybe I have a copy of your social security card for security purposes. And that would be unstructured data that's still in the database as an image or some sort of attachment. What we're hoping for when we create these databases is certainly a way of collecting and organizing and storing the data itself. That's definitely important. But the second, probably more important feature is what can we do with that data? Just having data doesn't do much for you. I collect all sorts of statistics on when I run or when I bike ride or when I swim, but the numbers themselves don't tell me much. What I need to look at is, am I getting faster over time? Or can I run a farther distance? Or is my heart rate lower as I get more and more practiced in the pool, right? I need to think about trends and patterns and whether a specific workout is doing more for me or less for me. And we'd want to do the same thing with some of these statistics. Maybe we can look at various classes and determine that students that are taking classes at a particular time in the morning don't get grades that are as good as people that are taking classes in the afternoon, or vice versa. And by the way, as an aside, it turns out there's not much correlation between class time and how students do. A lot of students self-select into the time that best serves them. So early classes and late classes, the grades tend to be fairly similar. But maybe we could glean something from the data and learn something interesting from it. So what we were hoping for is not just organization of the data in a structured format that works and make sure that all the data is interrelated, but also then getting something out of it, information. And one of our goals later in the semester, we'll be talking about queries, where we're asking questions of the data and getting valuable information from that data. And that's one of your goals at the end of the semester, is to then visualize some of that information so that you can present it to someone in a really appealing format that makes it easy to understand and valuable to them. The last thing that we need to talk about from a definition standpoint today is metadata. Metadata is the data that describes the data. You've used the term meta before, it's in a lot of memes. Meta just means it's kind of outside of the thing itself. So in our term, metadata is how do we describe the data that we're actually putting into our databases and manipulating inside our databases. And we'll see an example of that here in the very next slide. If we were going to create a class roster, this is some of the information that I think might be relevant for that data inside a database. We'd probably want some information about the courses. So we'd have a course name. We might have a section, and that might be some sort of numeric value. We'd probably have the semester the class is offered. So this class, I only teach in the spring, but I had a spring 2020 class. Now I have a spring 2021 class. We'd also probably have some sort of unique identifier. There's a unique identifier in Howdy that's like a 5-digit number that's relevant to this class. So we probably have some sort of unique identifier. Maybe something in terms of a major. So what major is the class representing? And it may not represent a major, but maybe it does. So maybe that's something that's optional. I don't know. Maybe some sort of GPA. So what's the GPA for a specific student that's enrolled in the class, right? So this is all the information to be in the table, and then you can look at how we describe all of that data. So for instance, the course is alphanumeric. It could have letters, it could have numbers, it might be words that are typed out, or in our case, ISTM 313 might be the designation for the course, right? So alphanumeric, could be letters and numbers. It looks like in this particular example, they're talking about a length of 30. So we got a lot of characters to describe a specific course. Doesn't look like there has to be a minimum or a maximum. This is just course ID and name. And the source where we're actually going to get that information is, according to this, some sort of academic unit. This is not information that's stored in the actual database itself. It's kind of stored tangential to the database to tell us about what's in the database. It's describing what you expect to see in a column in a table, if you're looking at a spreadsheet or if you're looking at a table in a database. So similarly, section, we're expecting that to be a whole number, an integer. It has a length of 1. You could have a section 1 or 2 or 3 or 4 or 9. Looks like that's about as big as this will accommodate. So 1 through 9, that's the most we could have in this table. This table is probably not designed for Texas A&M. We know there's some classes here at school that have 20, 30 lab sections. So they would have to accommodate us a larger number for sections. But for this particular example, they're capping it at 1 through 9 for sections. And then the specific section number and where that information is coming from. And you can kind of look through the rest of the table and glean what metadata is doing. It's describing what is allowed, what you're expecting in an actual table that stores data in a database. So we're going to spend a lot of time on metadata. It's important for a well-structured database that you know what kind of data you're storing and that you scope it or control it as tightly as you can. I don't want to allow for somebody to type section Q. I want them to type a number, and I want it to be a whole number. I don't want there to be 2.3 sections. That doesn't make any sense. This is something I discuss a lot in my programming class. We do an example where I design a program that collects a food order. And I have to look out for students that allow people to order 2.3 sandwiches or 4.7 pizzas. That doesn't actually work, right? You have to order a whole unit of something that you're going to buy from a restaurant. So I have to make sure that they scope their variables in their programs. We need to scope the information in our databases to accommodate the right kind of information that we expect to see stored in our data. So we're going to look a lot at metadata as we get farther into the semester and start to create databases themselves. Historically, how we've managed data has been file processing, where an individual or a group of people or a department creates a spreadsheet or a database of their own, some sort of file system to store information about somebody. Think old school filing cabinets, where you'd have to flip through a bunch of different yellow manila folders to find something on somebody. And think about how inefficient that is for lots of different reasons. One of the issues we might have is that we might have program data dependence, where the program stores data in its own way, but that's the only way that you can get to that data is using that program. So if I'm using an older software package and I want to actually move that data to a newer software package, that's a challenge to do so. And I've actually been involved in the real world in some of those projects, and moving data from old school, either database packages or spreadsheets or somebody's notes in a WordPad file can be really, really onerous. So that's one of the major issues, is how you have the information stored and whether it is interchangeable with other programs and interrelated to those other programs. You also definitely have an issue with data duplication. If I'm storing information about you in my department, accounting, because I'm worried about how you're paying bills, but somebody else is storing information about you in human resources because they're interested in what your background was before you joined the company, well, how do we keep those two pieces of information kind of synced up with one another, right? So you potentially have lots of information that's stored in two different places that's duplicated, and when it changes in one place, how do you make sure that it changes in the other place? Yeah. And you've probably experienced that, because as good as we do a job here at the university, it's not perfect. There have been many circumstances for me personally where I've updated information on one system and it still shows up wrong in other systems. And the best example I can think of, and we might still actually encounter it this semester, is my first name is Ted, but my actual given name is Edward. I'm Edward Boone II. And I never go by that name, but it is my formal name, which means that it is in something like 16 different databases here at Texas A&M, including the database that feeds eCampus. And so I'll get emails from students that are addressed to somebody that I don't relate to, Edward Boone. I'm wondering why I'm getting emails from my dad. I don't know how to fix that sometimes, right? I fix it in one system. I think that it's going to fix other systems, but they're not all actually interrelated. It's not just one central repository of information. And just because it updates in one place doesn't mean that it updates someplace else. And you've all had that experience in other situations as well. It can be really frustrating. So that's something we'd like to solve with modern database solutions. There may be some limited data sharing. Like I said, some programs don't talk nicely to others. We've gotten a lot better than that. In 2021, we do pretty well with programs that have interdependencies and can actually communicate with one another, but it's still something worth thinking about. Certainly, we could be worried about lengthy development times. You may be reinventing the wheel, where you're creating entire solutions for problems that you don't need to create because they've already been created someplace else. And you really could just use their solution and just tweak it a little bit for your needs. And honestly, the biggest issue is that this is just costly. There's an estimate that 80% of an information systems budget is managing the various programs that we have. Well, what if we could go from 6 different programs and 6 different departments to one consolidated program that serves everybody? You can imagine the economies of scale if we could come up with a singular solution that everybody could use. So that's one of the major driving forces when we get down to it, is price. Let's get this thing to the cheapest possible price, which means some commonality. Like I said earlier, data dependency and data redundancy are certainly a concern with how we've done things before. If we are dealing with separate programs, then every programmer and every application developer has to maintain his or her own data, and the program needs to include all of the metadata inside it. And so this gets to be kind of clunky. There's no central control. One of the issues we have here also at the university is there's some information that we are not allowed to reveal about our students, right? Some of your information is private, maybe it's protected by HIPAA or FERPA. And so we need to be really careful how we store that information and where we store it. If we can come up with a central repository for all of our information, we have better control. If we have a bunch of different silos where the information is located, then that control starts to break down. We certainly have some worries there. Here, pictorially is what I was talking about with the duplicate data. You can imagine that we have some sort of customer master file in the orders department for a company, and we have a different customer master file for the accounting department. They're all the same customers, but we're doing different things with the data. So historically, they might exist in different programs, and they wouldn't necessarily talk to one another, and as a consequence, they would fall out of sync with one another. And you personally have experienced this if you've ever done any group projects with students where you're doing some sort of paper you're working on together. In just a few years ago, we didn't really have great tools to do that. So you may have written part of a Word document, sent it in an email to somebody, and then waited for them to contribute their part and send it back to you. What if in the meantime, you made edits to the first document? The person you sent it to probably can't see those edits. And so how do you get those things to get back together? Now, some of you might use some of the more modern tools in word processing. I know Google Docs does a great job of this, where you could share the document, and then 2 or more people could be typing on the same document at the same time. And that's really cool, right? You see the different cursor, people are editing, and you're working on things together, maybe while you're on the phone or you're on a video conference call. That's a neat way of working on something. But think about what happened there is instead of having 2 different files that are kind of moving back and forth, you've got one consolidated location where multiple people are working on the same file at the same time. So we eliminate that duplicate data. Getting rid of duplicate data is a huge advantage for the everyday worker in terms of making sure that nobody is doing things more than once, that everything is actually up to date, and everybody has the same information at the exact same time. And it's going to be one of our major goals that we're trying to accomplish as we talk through this database process. Already talked about this, but the problems with data redundancy. If you have duplicate data, it's taken up a bunch of space. It's hard to reconcile which information is right. If there's a problem with data, you have some inconsistencies, and then you got to figure out what to do with those inconsistencies. Which information is the more up-to-date piece of information? And that can be really, really challenging. And I should be clear, even in modern databases, sometimes data integrity is still an issue, because there might be situations where we're getting 2 people that are just banging on the same piece of data at the exact same moment in time, and we got to figure out what to do about it. Not too long ago, my wife and I were both trying to use frequent flyer miles to buy airline tickets to go someplace. We're going to take advantage of the cheaper price, right? We're going to spend some miles instead of spend some actual dollars. But what kept on happening is we were yelling back and forth at each other in our house. Because I'd say, okay, I got it. And she'd say, well, it won't let me buy a ticket now. I'm like, oh, that's weird. Let me back out. And then she'd say, okay, wait a minute. No, I've got it. Well, now I can't do it. What's happening? We're both competing for the exact same last leftover miles ticket. And it literally, we're trying to hit the computer at the exact same time. Of course, it won't let us. So one of us is a millisecond faster or slower than the other. And that person gets it. And the other person gets a message that says, sorry, there are no more tickets available. So modern databases have to think about this and have to manage that sort of thing. And it might be at the millisecond or the nanosecond where it has to figure out which piece of information is more correct than the other. So, solution to all these dilemmas that I've just been talking about is to come up with this database approach. Ideally, a central repository for all of the data that is still interrelated. So we still have a database here at A&M, something like single sign-on or Howdy, that has a lot of information that serves a variety of different needs, but it is still about one big problem. It is how we manage Texas A&M University, how we manage our students here, or our finances here, or our classes here, or what have you. So it's still scoped, but fairly broad in scope, where we got the big bucket with lots of data that's put in there, well organized, good definitions in terms of the metadata, and then various departments and units and individuals can tap into that database to use the information that's relevant to them. You as students can sign on to Howdy and you can see your classes and your grades and your schedule. I can sign into Howdy and see my classes and my students in my classes and the grades they're getting in those classes. We're tapping into the same database. We have different uses for that database, but because we're using the same source, we don't have to worry about data redundancy. We don't have to worry about any kind of logic issues. We're all using the exact same source, and it's managed by experts in one place. So we don't have to have a lot of different experts doing lots of different things. Everything works better if we come up with this data approach. Coming up with that data approach is hard, and that's why we're going to spend an entire semester talking about this stuff. But if you can do it, if you can plan ahead and come up with good structure, come up with a good plan, the end result is way better than what we've been dealing with in the past. So we're going to talk about database management systems, but first we're going to talk about some of the structure that goes into any database management program. The idea here is big bucket on the right side of your slides, right? It's this central database that contains all of the information that is relevant for our large scale problem. Some sort of database management system that sits in front of that bucket that manages how the information flows in and flows out of that storage, organizes it, controls it, allows for certain things to go in and not others, allows for certain information to be revealed to certain programs or people, but not others. And then various programs on the left-hand side that are designed to interface with that database management system to use the information that is relevant to them, to have access to only the data points that they're supposed to have access to. When I log into Howdy, I can see information about you in my class. I have no idea what other classes you're enrolled in. I have no idea what grades you've gotten. I don't know what your GPA is. I don't know how many credits you've taken. I don't know your permanent address. That information isn't relevant to me as an instructor. The program that I use, in this case a web interface, taps into the database management system that only reveals the information that is relevant to my role at the university. So we have the big bucket that's got all that information. I can only see the parts of it that I need to see. You can only see the parts of it that you need to see. And that's pretty amazing if you think about how many moving parts there have to be to get all this working properly. The big advantages: we get rid of program data dependence. Everything can talk to this DBMS. It has a common language, and as long as you know what that common language is, you can kind of hook into that program and use it any way you want, which is really cool. So we don't have to worry about if I want to use Excel to get information, I can. If I want to use a web interface, absolutely you can. If you want to use Access, Microsoft Access, a database program, to tap into Howdy and get information out of it, sure. If you want to write a Python program to get information out of Howdy, yeah, you can do that. If you have permissions, you can use whatever program and interface that you want. You can just hook in to the database behind the scenes and grab the information that is relevant to you that you have permission to see. We can plan for things like particular data redundancy. Maybe we allow for some places where multiple data points are stored in different locations. Maybe that's allowed sometimes. And then on a schedule, some sort of regular basis, we resolve those issues. We say, okay, we've got this situation where we've got two pieces of information that look kind of similar. How do we merge those? Or how do we decide that this one's the right one and this one we throw in the garbage? We could have a program that actually manages that. We'll have much better consistency of our information. We'll have obviously much better data sharing because everybody has access to the same central repository. We should see much better application development and productivity. Maybe there's some situations where now that we have this central repository, we're thinking about data in different ways. Wait a minute, I've got this piece of information over here and this piece of information that used to be way far away right next to it. If I put those two things together, now I've got a really interesting report that's useful. So we might come up with some really clever applications that show us some cool stuff. And that's often the case in the real world. We are able to enforce common standards, the way that we store information. We can have a rigid structure for that so that there are no exceptions to the rule in terms of how we store information. Now, sometimes that results in some really weird situations. I deal a lot with some master's students in the MIS program, and we have a lot of international students in that program. And some of them are from India, and some of them actually don't have formal second names. They have just a single name. So we're used to John Smith in the US, but certainly other cultures don't do that. but the database is expecting an information entry in both your first name and your last name spot. So we have people that have a dot or a period for either their first name or their last name in some of our databases. When I first got here, I thought, what's going on here? The system does not accommodate for someone who only has a single name. And so we have to do something with that. And so we put a period in there to say, they don't actually have this, but we have to fill in the gap, right? So sometimes you get some weird stuff if you have these enforcements of standards. Usually that's a good rule, but sometimes it causes some issues. Again, overall, we're expecting better data quality. We should expect better accessibility, better program maintenance. You can see just from a common sense standpoint, this solution has some significant advantages over what we might have done in the past. That doesn't mean, of course, that all is perfect. When we use the database approach to solve some of our data management situations, we definitely have some costs involved and some risks. If you're going to do this, you need to have specialized personnel. Again, we're going to spend an entire semester talking about how we structure data, and you guys will only be getting just a taste tester of what it takes to actually create and manage an enterprise level database. So you can imagine how well-trained and well-paid an expert in these fields must be. And it's important you have that. Whereas in the past, if you know how to use a spreadsheet, you could create your own solution potentially. So this definitely requires specialized personnel, which does have a cost involved. It does obviously involve installation and management of more equipment and more software and making sure that there are incompatibilities that are solved, right? So you could use a Mac or you could use a PC and still tap into this information. There may be some conversion costs as you move from old systems to new systems, and conversion costs can be really high. When I worked for Zeneca Pharmaceuticals, again, this was 20 years ago, they were just adopting SAP in one of their plants. And the cost of moving from their old system to SAP over an 18-month period was something like $5 million. That was just moving from one system to another in one location in the US. And this is a multinational company. So you can imagine how much it costs just to move stuff from one place to another potentially. You do need to plan for explicit backup and recovery. All of a sudden, the central repository is the only place where things are stored. So making sure that that information is properly backed up and stored and has plans for recovery in case something goes wrong is really, really critical. If you're going to entrust all of your data to one place, you want that one place to be really, really safe and secure. So we need to be careful about that. And it could cause some ill will in some of the organizations that have done things differently in the past, right? Because this does require everybody to follow the same rules. Maybe you've done something one way and now you're being asked to do it a different way, and you'll probably get some pushback for that. You guys will experience that out in the real world. That's going to be your lives as you move forward. And we continually change the systems that you get used to make them work better. Think about how much people lose their minds when Instagram moves a button from the bottom of the screen to the upper right-hand side of the screen, right? And then think about what happens when you get older and grumpier and they're messing with your workflow. That gets people pretty upset for sure. I'm seeing a brief chat, so this is actually a good opportunity for me to take a breather from the slides. James Warman asked, would you say that overall, with a database approach, management costs are lower or higher than other options? Beyond the initial setup, where you have to get everything up and running, you have to get buy-in from the various departments, you have to really plan how the information is going to be stored, what information you need, all those sorts of things. The long stream costs are far lower. Once you have a system like this in place, everything works better. Everything has much better storage and backup. There's an opportunity to come up with solutions you might not have had before. There's less responsibility in the individual departments for things that really they are not experts in. What they want to do is just use the data to come up with information to solve their problems. They don't really need to be data management experts. So in terms of long-term costs, absolutely much less than if you were dealing with a non-database management approach, which is one of the reasons why you guys are probably taking this class. Is this is a good idea, understanding how this stuff works and then being able to use it, even at an individual level, but certainly at an organizational level, should reap benefits in the medium to long term for sure, and might actually even provide some short-term benefits just in terms of organization and structure and your thought process in terms of what kind of data you have and how it works for you. Great question. Thank you.
Great. Thank you.
All right, so what are some of the common elements of the database approach? Well, first, we need to come up with some data models, and that's what we're going to spend the first part of the semester talking about, is the way we are thinking about how most data can be structured. And we're going to do that with data models and entities. Okay, and then we're going to talk about relationships as part of that. So all of this is going to be stuff we're doing here for the first, I don't know, third of the semester. So data models. How can you draw pictures that capture how your data interrelates? So how do students interrelate with classes, and how do classes interrelate with professors, and how do classes interrelate with departments, and how does all of that interrelate with human resources or finance or whatever? We're going to have to sort of figure out how all these different pieces in an organization are related to one another. We spend a lot of time thinking about that. So we're going to try to come up with some drawings, some pictures, some diagrams, some charts to figure out how does the data actually work. And I love this class because it absolutely makes true the famous saying, a picture is worth 1,000 words. The kinds of things that we can just draw in a simple picture can tell an enormous and very important and very detailed, very clear story. We need to be careful about it. We need to use absolutely the right symbology and the right structure to tell the exact story we're trying to tell. But once we learn that structure, we learn that language, we can put a pictorial solution in place that tells you everything you need to know, which is really amazing. So we'll spend a lot of time doing that. The parts of the picture are going to be entities, which we should think of as nouns. They are the thing that we're putting into the system, a person or a place or an object or an event, a product. It could be a sale, it could be an order. There are things that you can think about that might move through the system. Those things are typically described by attributes. So in a database, a student might be an entity. You exist here at Texas A&M. An attribute is how I describe you. Your last name, your first name, your UIN, your address, your phone number, your major, all those sorts of things are how I describe you as an individual entity. Right now, what we're going to be talking about in the diagram is just the generic entity. So our diagram is not going to have John Smith, whose UIN is 123004567. I don't know anything about the individuals. They're going to fit into this diagram. The diagram is just going to have student and maybe some attributes that we expect from a student, like last name, first name, UIN. But we're not going to be filling in those specific details. The diagram is for any generic entry into the database. We're going to describing really the metadata that's going to be going into these things. And depending on where we are with the diagram, we might even leave the attributes out. If I give you a diagram and what it says in a rectangular box is student, you already know as students what I'm talking about. You're talking about an individual that's taking classes at a school, and you probably expect that they have names and phone numbers and addresses and GPAs and all those sorts of things. You know something about that entity. So in some of our diagrams, all it's going to have is the entity represented in a rectangle. Sometimes it will have additional attributes to tell you some things about that entity, just to illustrate that we have some descriptors for that entity. It will depend on what kind of diagram we're drawing. We're going to connect those entities with relationships. So a student has a relationship with a course. You're enrolled in a particular course. And you probably have a relationship with the semester, what, 2, 3, 4, 5 classes, right? And every semester you have those relationships. So we're going to draw a picture that shows that students have relationships with classes, classes have relationships with students. And there are all sorts of relationships we can have. And so most of them that we're going to be talking about are one-to-many. So there's one thing on this side that's related to lots of things over here, or many-to-many. Lots of classes, lots of students, and they have relationships with each other. And we'll have to solve how we draw that, which again, we'll spend a lot of time on this semester. There are some situations where you might have things like one-to-one relationships. So if I were important enough at Mays, and I'm not, I might have an assigned parking spot, right? That's a one-to-one relationship. Either you have it or you don't have it. Each parking spot that has an assignment has one person assigned to it. Each person that has an assigned parking spot gets one parking spot. So we'll have some one-to-ones, we'll have some one-to-manys, and we'll have some many-to-manys. And we'll talk about how we draw those pictures and how we enforce some of those rules. We'll even talk about things like optional relationships and mandatory. So we might have rules that say you have to be enrolled in at least one class to be considered a student in our database. If you're not enrolled in any classes, you're not really a student. But we might have rules that say you can have 0 or 1 or more things. So we'll talk about these optional rules or mandatory rules as we move through databases. All of this leads us into what is called a relational database. If you are creating a database that has entities and relationships between those entities that are enforced as one-to-one relationships, one-to-many relationships, or many-to-many relationships, you're designing a relational database. And that's the only kind of database that we are talking about in this class. There are databases typically in the really large database arena that have moved away from the relational database structure. They do things differently. That is outside the scope of this course. So I know a little bit about the very large databases, but the way they operate is quite different than our structure. However, if you understand how a relational database works, that still would feed your understanding of how they then use these very large databases to do similar sorts of things, but they kind of break down the structure because they are just so large, they need to approach it a slightly different way. All right, so another question from Allison Campbell. She said, why is there an N on the right side with the many-to-many instead of M? Because the way they are writing this is, this could be that there has to be 3 on one side and 5 on the other. So you have to have 2 different letters, M on one side and N on the other to represent that. They may have slightly different ratios. So M and N are both, there could be a lot on this side and there could be a lot on that side. If it's a 1, that's obvious. The most it can be is 1 on one side and many on the other. But here it's 2 different manys. And I'm not saying that it has to be 5 and 5 or 7 and 7 or 12 and 12. I'm saying some number over here and some number that might be a different number over here. Great question as far as the nomenclature. And we're going to have a lot of nomenclature that we're going to be talking about this class. This class is more me delivering some content to you, but starting next week, we're gonna have a lot more back and forth where we're gonna be talking about the nomenclature and making sure we're getting it straight. But thanks for the question today, I appreciate it. There are some other terms that you're gonna see as we move through the semester, or you might have already seen out there in the real world, things like case tools. This is an abbreviation for computer-aided software engineering. We're not using this, but it is something you do see when you see database development. You may hear a term called repository. This is where we store all of our metadata. It's basically the rules for all of the data that go into our database, a repository for all of the different data rules. Obviously, we've talked about database management systems, how do we manage our data. The database is where we're actually storing the data. The programs are what we're using to get at our data. Now, we're not going to be doing too much in terms of front-end programs that access the data, but one way of thinking about our visualization tool, Tableau, at the end of the semester, is it is tapping into a data source and then using it for visualization. So it's an application program that's tapping into a database management system underneath it. Obviously, user interface, what kind of either text or graphical display are we using to get to the information to either input or output it? We're going to talk about the roles of database administrators. Some of your kind of mini job this semester is to be a database administrator for your own database. We're going to eventually create some databases on a server, and you'll be managing those yourselves. You're also going to be working as a software developer. You're going to be coming up with the solutions to some of these problems. Now, I'm not going to ask you to actually write any code or anything, but you're still going to be involved in coming up with some interfaces and getting some information out of the data that we're going to have stored in these databases. And the goal would be, in the real world, of course, to have legit programmers designing interfaces that then allow end users to use their solution. So again, think about how you can manipulate your data here at Texas A&M through the Howdy system, or you can sign up for an hour in the weight room at the rec center using their rec sports webpage interface, right? How do you actually interact with the data at an institution or an organization is probably through an interface that was designed by a software developer, systems developer. And here's pictorially what we're talking about. What we're focused on for the first part of the semester is how do we describe the information that goes into this database cylinder? And then how does the database management system enforce the rules to make sure that the data that goes into or out of this database fits that particular structure? So we are focused entirely on the bottom right-hand part of this picture for the first third of the semester. We're not really going to be using a separate repository. It's kind of built into our database management system as we talk through the first part of the semester. But we will obviously be talking a lot about metadata. And then when you get to the later part of the semester, you'll be doing a little bit of user interface and application programs for asking questions of the data, doing some querying, and then doing some visualization. So we'll get into all of this as we move through the material this spring. Now, most databases today are going to be predicated upon a network, right? It makes sense to have a computer network where all of the data is stored on a server someplace in a basement somewhere or some sort of central computer center, and then various users can tap into that database server using a network. That does not have to be the case. We could absolutely be in a situation where all of you are actually writing your databases on your own individual devices, and then different users are accessing it. But the whole point is, by coming up with a central repository, different users with different needs should be able to access the data at the same time. So one of the things that requires is a network of some sort. This is a two-tier network where we're tapping into our database using some sort of local area network. There may be a multi-tiered environment where people are using a web interface to tap into a web server, which then talks to a database server, which then talks to the depository. And so, repository. So when we talk about something like Howdy, that's a multi-tiered environment because it requires a web interface and a database interface to communicate the information back and forth from the user to the data behind the scenes. And this is what that looks like, three-tier, where you're communicating through a web server and then communicating with the database management server. And the great thing about this solution is it further simplifies the interface. The interface is just a web interface. All of us are familiar with how a web browser works. There's a lot of common tools we expect to see in our web browser interface. Everybody has a web browser, so we don't need to install any separate clients or any of those sorts of things. So this is a really cool solution that most organizations have started to adopt as we move forward in time. Now, I will say sometimes this isn't the best solution. I teach an elective for supply chain in SAP. They have a standalone client that you can install on your PC or your Mac to access a server. Our server happens to be in Milwaukee. That client works great, very, very robust, has lots of features. They have also developed a web interface. I think the web interface is garbage. It's very slow, it's disorganized, it doesn't have all of the same feature set, it's hard to find the features. So in that class, even though we have this either three-tier or two-tier solution, I still teach it as a two-tier architecture because the client is so much more well-developed than their web interface. They may change that in the future, I don't know, but right now I'm not a fan. That's a personal choice, but since I'm the boss in that class, I get to choose how we work through that class. Some of the common applications we see for database, ERP. I teach an ERP class, I teach an SAP programming class, but SAP is an ERP or Enterprise Resource Planning program where we're trying to integrate all the various enterprise functions. How do we make things? How do we buy things? How do we sell things? How do we move things around in our company? And then how do we track the money as it moves back and forth as well? Might also be managing things like human resources inside those systems. You could imagine something like a data warehouse where we're putting all of our historical data into a storage center, all of the things we've done in our company, so that later on we can look and say, hey, did something interesting happen in a particular time frame or at a particular location or for a particular product, or when we made a particular advertising campaign? Might be able to dig into all this data to glean information that you wouldn't otherwise have. So data warehouses obviously use some sort of database application. And there are lots of other potential applications that use database management systems for good use. So where are we going from here? Well, to start with, we really got to get into the modeling of the data. So before we actually use any data, create any databases, ask any questions of the data, we got to figure out how do we structure data in the first place. So we're going to spend a bunch of time over the next couple of weeks dealing with what we call entity relationship diagrams. Think about that earlier slide. We talked about entities, they're nouns that go into our data, and then relationships, how those entities relate to one another. And I said we're going to draw pictures, entity relationship diagrams, or ERDs. We'll start with basic ERDs, and then we'll get to an enhanced ERD structure in a few weeks. Then we will move to what's called logical modeling, which is called a relational schema. And really, ideally, that is not much of a transition. We can move from an ERD to a relational schema where we're programming it for the database without much difference. However, realistically, that ends up not happening. There are things that we have in our diagrams that are perfect, they're idealized, and then it turns out that the specific database program we're using doesn't accommodate the way we've structured the data. So there's a transition from ERD to relational schema where we're basically taking the idealized perfect picture of our data and making it work given the constraints of whatever software that we are actually using. And there's almost always some sort of constraint that we have to work around. So we'll spend some time on that, where we're transitioning from our ERDs to our relational schemas. And then we'll actually build databases. So we'll create stuff inside a SQL Server or an Access database, maybe both, kind of play around with how the structures actually work. Again, we'll see that once you start plugging in real data, our idealized pictures, either in our ERD or even in our relational schema, might not work the way we wanted them to. And we might have to further relax some of our constraints or change some of our assumptions to get things to work properly. So there's always a little bit of give and take as we move through these things, and reality asserts itself. And we'll talk about that as we get into the last third of the semester. We'll be querying our data to get interesting results from it. And then I set you guys loose on your final projects where you tackle some sort of real world problem, which we'll talk about probably next week, using real world data that you've structured, that you've queried, and then you've visualized using Tableau. So lots of cool stuff happening as we move through the semester. I'm really excited. I think you guys are gonna have a really good time this semester. It's certainly gonna be hard. We've got a lot of stuff to do, but I think if you stick with me, you're gonna find it enjoyable. Okay, so that is our lecture, chapter 1, okay? Any questions about what I just lectured about? Make sense? Kind of just a roadmap for what we're going to be doing. Okay, here's where we're going from here from a schedule standpoint. I'm going to wrap up today in about 5 minutes. After we are done today, what I'm asking you to do before next Tuesday is to look through the next PowerPoint slide. So the next PowerPoint slide is lecture 2, which has to do with, I'm going to actually go look at it myself, the modeling data in the organization. I want you to just look through those slides. You don't have to learn it on your own. I'm going to talk through them, but please make sure you've looked through the entire slide deck before you visit with me next Tuesday to take a look at some of the pictures, look at some of the terms. You might look at a slide and say, okay, that kind of makes sense. I understand that. Great. But if you're looking at something and saying, nope, doesn't make sense to me. That's what my job is to fill in those gaps next week. But I need you to look at it first. And we're going to start working through one of the workbooks. If you go and look online, there is a modeling workbook on eCampus. Modeling workbook is a big PDF file. It's 14 pages. And this is what we're going to be using for our in-class exercises. And we are specifically going to try to work through together, either on Tuesday or Tuesday and Thursday next week, at least the first 4 problems in the workbook. So I am going to be cold calling on people on Tuesday, assuming you've done something about these 4 questions. So I want you to be thinking about how you would draw the entities and relationships for each scenario. Absolutely, your answer could be, I drew this, I know it's not right, I'm not quite sure how to approach this, I don't have all the symbology right, but this is what I tried. Your answer is not allowed to be, I didn't draw anything, I don't know what to do. You got to try. So write down some answers for problems 1 through 4 between now and next Tuesday, and then we'll talk about it as a group and sort of talk about where you guys landed and what's a good solution, what's a bad solution. Some of these questions have multiple approaches. And then we'll talk about what makes one approach better or more realistic or more detailed than another. So there isn't always just one answer. So put something down. Chances are you're at least going in the right direction. And if you're not, that's a learning opportunity for you and other people in the classroom to say, you know, what you did there isn't quite what we were looking for, but we're gonna get there by talking about. Does that make sense to everybody? So you got two things you got to do. I want you to look through PowerPoint slides, and I want you to work through the first 4 problems in the modeling workbook. Sound good?
I have a question. Where are your PowerPoint slides? I feel like there's a lot of different tabs that you have on
eCampus?
Yes.
1 second. Lectures, under course content. So if you come here to lectures, you'll see the ISTM 313 lectures. Okay, and this one is just a big zip file you can download and grab all of them. So lectures, PowerPoint slides are up in the lectures section. I will be adding these Zoom lectures to the video section on YouTube, and then the workbooks are in the workbook section. So I'm asking you to grab this modeling workbook and work through the first 4 problems in the modeling workbook. We haven't gotten to the rest of this stuff yet, like the database and the groups and the group projects course, nothing on exams yet. We're on these first 3. So grab the YouTube or the PowerPoint slides in the lecture section, watch the videos if you've missed something, and then grab that workbook and work for the first 4 problems for next time. Yeah, and yes, it's in a zip file because otherwise I have to upload every single file separately. So you just have to grab it and then extract the files out of it.
Professor, I had a quick question.
Yeah.
So I was looking through your syllabus, and I guess so these the Tableau videos, you haven't really, I guess, touched on those this time, but I saw there was one due for today. We didn't.
Yeah, so I did talk about that on our first meeting. The way that the Tableau works is that you guys have access to those Lynda videos.
Right.
And you are expected to be watching them as we move through the semester, so that by the time you're going to be using Tableau for your group projects, you have learned the techniques that are available in Tableau. Now, I'm not mandating that. I'm suggesting that if you do a video or 2 every week, then it's really easy. It only takes a couple minutes of your time every week. And then at the end of the semester, you're good to go. I know, because I know students, that almost everybody I'm looking at, what are you about to do? Nothing in Lynda until we've got 2 weeks before the end of the semester, and then you're going to cram it. I highly recommend you don't do that. If you watch the Tableau stuff and you're working through it, it's actually going to fill in some of the insights that you need for some of the earlier database stuff. So it's going to be useful early, and it will save you time in the long run. But look, there are only so many things that I can police. So I am strongly recommending that you spend a couple minutes every week watching those Lynda videos based on the schedule in the syllabus. That's the best I can do. I know that you guys aren't going to listen to me, and that's okay. Other questions for me?
Yes, I had one. For the homework problems that you want us to work out, is that going to require us to do the screen sharing software you were talking about next week?
For the in-class exercises, we're going to be doing some screen sharing. So I'm talking about the workbook problems 1 through 4. So when I cold call somebody, what I'm expecting is that you're going to share your screen and say, here's the diagram I came up for problem 1. So that's the screen sharing part of things. That's just interaction with me in the classroom for our in-class exercises, which will be part of your homework grade. And typically what's going to happen is we'll work through as much as we can in the classroom. And I might say, hey, you know what? We didn't get to problem 4. I'm going to put a place up on eCampus for you to submit that. You could submit that for a homework grade. So the homework's kind of be kind of an organic thing where if we either didn't solve something completely or we didn't get to something during our in-class exercises, I might challenge you to work through that, or I might give you a new problem that's related to something we've talked about as an additional challenge. And then homeworks are just going to be something you submit on eCampus so that I can see them and make sure you're working through the material.
Okay, thank you.
Of course.
For the homeworks where you might call on us and we have to share our screens, are you going to want us to already have it completely worked out for everything?
I expect you to have something. If I call on you and you say, I've got nothing, you don't get credit for contributing, right? But if you say, I got a diagram, I don't know if it's right or not, but this is what I tried, you get credit. And so it's not about necessarily having the right answer. It's about you definitely looked at it ahead of time. So again,
Okay.
if you come to class next Tuesday and you haven't looked at the problems and you are the lucky person that gets their name called and you got nothing to show me, I'm not giving you credit for contributing that day. You have to be here,
Okay.
and then you have to actually be willing to contribute something. And you need to show that you already have something. You're not just kind of making it up on the fly.
Right. I think what I was getting at is, should we do all of our homework on like our computer, or could we write it out in our notebook? And then if you call on us, we can quickly write it out live in the class from like our copy.
That's a good question. Yeah, and that's why I appreciate the question, because I'm sure you're trying to work through that. I suppose I would want it where you could display it to us pretty quickly, not just be working through it, because I don't think a lot of us are going to want to just watch you draw on a screen, when I'm calling on you. So even if you work it out on a piece of paper, you may then need to have a screenshot of that or something so that it's available on your computer and you can show it to us if I call on you.
Okay.
I
So
appreciate that question. I hadn't really thought through it. So yeah, and again, I know I haven't used it yet, but I saw on the share screen for Zoom now that apparently I can share my iPhone or iPad as like a separate interface. That's really cool. I haven't done it yet, but if you want to do something like that, if you have a different screen you're going to share, I don't know. We're going to sort of figure this stuff out, and next Tuesday is going to be the first time we do it. So it might be a little bit bumpy the first time around, but something where you're ready to go and you can show stuff to us, not you're working through it live with us watching.
Okay, so maybe you'd be okay with if we took a picture and like had it of like our actual work,
Sure.
where we could just like pull up that picture.
That would be fine.
Okay.
Absolutely. Yeah. So you'd rather do stuff on pen and paper that's going to then require taking a photo and then having that available to talk about. And then we can obviously use the whiteboard here in Zoom to draw on things and all that sort of stuff. So, and I may even ask people to do that. I might ask for Allison to show us her beautiful snapshot of the most glorious answer for number 1 we've ever seen. And then I say to Jacob, draw all over this and tell us why it's the worst thing you've ever seen and how you would make it better. I don't know, right? We have this opportunity where we can try to be as engaged as we possibly can in this virtual environment. We're going to try it and see what works.
Thank you.
You guys are going to let me know kind of what works and what doesn't work, and we'll find a common ground. Anything else? Thank you guys so much for being here today. I really appreciate it. Thank you for great questions. I hope you found the lecture interesting. Again, I have recorded this, so I will post this on YouTube and then post a link. Well, I won't post the link, but if you go to the YouTube channel, you'll see these lectures start to show up. So if you want to rewatch it because you weren't here for the whole thing, or you think you missed something, or you just want to review when we get to exams, they'll be there for you. Okay, so next Tuesday, I'll see you guys for the next lectures, and then we'll start working through the problems in the workbook. Have a great weekend, and I'll see you guys next week. Bye, everybody.
Thank you.